Hi, so most of what I'll report on is joint work with Gidon Amir, who is in Israel, and Fedia Nazarov, who is in Ohio. The special case, the linear case P equals 2 is in paper that appeared last year with Dor Elboim and Ron Peretz. And there's actually some new work that is not here, building on this, which I want to mention later, and that's with the two students at Tigwa, Chen Yu Gan. Can you stand up? And I wonder if is Junchi around? And Junchi Zuo. So they actually built on this and did something even harder. So I'll come to it later. So let's start by talking about the classical averaging. So although most classically it's done synchronously, here we will focus on the asynchronous case. So we have a graph. This graph, you can think of it as a social network or a sensor network. And every vertex has an opinion or a measurement. So every vertex at each time, so t here will be discrete. So time 1, 2, every time. A vertex is chosen at random. And that vertex updates its opinion to just be the average of the neighbor. So this symbol means the sum over all W that are neighbor of the vertex BT we chose, and it updates to the average of the neighbors. Now, you can also do this synchronously. Everyone updates at the same time, and then you're really just multiplying the opinions by a matrix. But this is more realistic. They don't have a common clock, so each one does it independently. And you can, this model can arise if each vertex has a clock, like a Poisson clock, and when that clock rings, the vertex updates. But here we're going, so that is FP, yes. Okay, so this is F time T plus 1 will be this. Yes, thank you. So it's an asynchronous version of the group dynamic studied by economists, and in the group dynamics, we do everything synchronously, right? So this is F time T plus 1 will be this average. Now, convergence to consensus is very easy in this case. It's really an exercise. So in the limit, all the opinions must be the same. An interesting variant I'll touch upon is when we have some boundary conditions, which in economics they call stubborn agents. So there are some vertices where the nodes do not change their opinion, they stick to their original opinion. And in that case, the limit will not be a consensus, but it will be the harmonic function with those stubborn agents as boundary values. And these theories are parallel, but not the same. Anyway, what we focus on is the time needed to converge to consensus. But of course, to actually reach consensus will only happen in the limit. So you fix a small epsilon. The value epsilon is not that important, and you want for the oscillation the max minus the min of st to go below this epsilon. Okay, so this tau epsilon is the epsilon consensus. So the question is, how does this depend on the graph and on the initial condition? But typically we'll ask for the worst case initial condition, given that it's bounded in 0, 1. Okay, so that's the averaging model. And here are some pictures of how that works. Say our graph is just a lattice, square in the lattice, and we start with opinions that are 0 on one side, 1 on the other side. And over time, the opinions get more and more equilibrated, and in the limit we will reach consensus. But here we did not run it long enough to get really close to consensus. So, so this model is pretty well understood. But I want to, before saying the results about it, I want to say what duality tells us about it. So this is duality of time reversal. So remember that ft at the vertex differs for ft minus 1 to vertex only if that vertex is what we chose to update it. All other vertices, the opinion stays the same. And at those vertices, we have the t and t minus 1 here should be the sum of, so say ft plus 1 is the average of the values ft. Now, tracing back, suppose we are interested in an opinion at the vertex v, and we want to see how that opinion arose. So this one is not the opinion, it is some measure valued process we will immediately discuss, the fragmentation process. So you have a vertex v. How did that opinion arose? Well, that we look at the last time the vertex was chosen, say here, and the opinion was the average of the neighbors. And I chose a graph where you just have two neighbors. And if you want to trace how those opinions arose, you have to go back till they were updated and so on. So if I want to understand how the opinion at time t is influenced by the opinions at time 0, it is just an average of those opinions. So the opinion at time t is an average of the opinions at time 0 with weights that are the result of this fragmentation process. Right? So mu t is a measure valued process. It starts at, so if we go back to this picture, what you see on this graph is how this measure evolves. So we start with measure 1 at the vertex v. Half of that mass is thrown to the two neighbors. And then there is a further fragmentation here. That half is divided quarter to the neighbor. And when we go to time back from t to 0, we have a measure which is, in this case, just a quarter, half quarter. On the general graph, it will be more complicated. And the measure time, the opinion at time t is just an average of the opinions based on that. So it's a fragmentation process. And again, to obtain mu s plus 1 from mu s, the mass at the vertex t minus s, so here you see the time reversal, is split equally among the neighbors of vt minus s in the graph G. Okay, so another, what? Because it's equal splitting because of the rule of the opinion dynamics, it's averaging with equal weights, right? When a vertex gets updated, its new opinion is an average, in our definition, it's an average with equal weights of the neighbors. You could put some transition matrix and have that be the averaging rule, and then the splitting will be according to that same matrix. Similarly here, if I want the probabilistic description of this process, we can consider a lazy random walk that, in this case, only moves with probability 1 over n. So we have a particle, and the particle usually stays in place because only we choose the location of the particle with probability 1 over n. And when it stays in place, when it is moving, it just moves to a uniform neighbor. So this is a random walk with which is very lazy, very delayed. And mu t, this fragmentation measure, is in fact the conditional distribution of xt given the choice of vertices to update. So XS itself is a simple random walk, very delayed, very easy to understand, but this conditioning makes it a little harder to understand. But still, the intuition is that the expectation time, the expected time to reach epsilon consensus should be roughly the mixing time of simple random walk, the time where the distribution of simple random walk is epsilon close to the stationary distribution. In this case, the stationary distribution is just proportional to the degrees. And there is another factor of n because of the laziness. So because we only move or update with probability 1 over n. So this intuition is rigorized in this paper that appeared in the journal Random Structure Algorithm last year. And so we get the mixing time and spectral gaps for your random walks on graphs are very well understood. There are several books on it, including one I wrote with David Levin and Elizabeth Wilmer. And we understand very well what are the extremal graphs. So the graph where the mixing is slowest with n vertices looks like a barbell. So there's a complete graph here, maybe n over 3. We have n over 3 nodes connecting, and another n over 3 here. So these are two complete graphs or cliques connected by a path of length n over 3. And this is the graph where it takes the most time for random walk to mix. So if I have simple random walk, it stays here for time n before it even visits this vertex. Then only with probability 1 over n it will make the brave step here, and another probability 1 over n it will go all the way. So the mixing time here is well known to be of order n cubed. Because kind of 3 rare events have to happen. You have to reach this vertex, you have to make the brave first move, and you have to cross all the way. So this is classical, which what this means, because we have this extra slowdown of n, is that on this graph, the consensus time is going to be of order n to the fourth. So this expectation tau epsilon is of order n to the fourth. There's some dependence on epsilon here, which is logarithmic, and also some logarithmic dependence on n, which arises. But so in this case, yeah, you can even remove this n, but that's a technicality. So as I wrote, this bound is sharp on a barbell graph. If you insist on the graph to have bounded degree, then you can just use a cycle. And on a cycle, of n nodes, the mixing time is squared. And so the consensus is going to be order n cubed. So all these things are to be expected. They're rigorized in that paper, but they're not surprising. The main point of this paper is actually understanding for the averaging process, what if you start instead of with the worst case initial opinions with IID initial opinions, with independent initial opinions. That considerably speeds up the process. But that's not what I want to focus on today. But I'm saying that paper has more than these rather simple things. Now, averaging, so here I have the t and the t minus 1 correct. Averaging can be thought as minimizing a local L2 energy, right? When I choose the value FTV, what is this value? It minimizes the average square distance to the neighbors, right? So I want to choose the y so that y minus the opinions of the neighbors of VT, when I add up these squares, that's minimized. We know that the number that minimizes the square distance to a list is the average of the list. Okay? So this is one perspective what averaging is. It's locally minimizing the L2 Dirichlet energy. Right? So that suggests that it's natural to look at other LPs. We know that's important. So so when we did the averaging, somehow we gave equal weight to all the gaps, and here other p weight differently the big gaps and the small gaps. So again, if you differentiate, you can see what is the new value will be one where if you take the new value minus the values of the neighbors, I hope you can see the bottom here, and add this up, the positive and the negative balance. So you see for p equals 2, we're just adding, we look at the value, and so those that are above it and those that are below it have to balance. Here we weight them with some power p minus 1. So if p is large, we are giving more weight to bigger gaps. And formally, a function is called harmonic on a graph if the value at the point is the average of the values of the neighbors. And it's p harmonic if it locally minimizes the LP energy. So exactly we're updating to make the new function p harmonic in the point Vt. And p harmonic can be characterized by this minimization or by by this differential condition. So p harmonic functions are a major topic in PDE. They're somewhat more subtle to analyze than um, classical harmonic function because of the nonlinearity in the equation. Any questions? All right. So so let's look again, say what we are really interested in. We have a P which is strictly between 1 and infinity. And we have some initial profile of opinions. And at each integer step, we have a new opinion, which is the same as the old opinion at all vertices, except at the vertex Vt, it is chosen to minimize the LP energy. Okay, that's the model we will be looking at. Now, this model turns out for p equals infinity, there's a meaningful limit. And when we take the limit to infinity of this dynamics, we get the following very simple dynamics, which I think is quite appealing. If you think of, someone updating their opinion on social network, one thing is, he has maybe 100 people he knows. Instead of looking at all their opinions and averaging them, he just looks, what's the spectrum of opinions of all my neighbors? So I have an interval where I see the other opinions. Let me put myself in the middle of this interval to be safe, right? So I'm going to be the average of the most left wing and most right wing of my neighbors, okay? So this is this dynamics, and it's again non-linear because of this max and min, but in some sense it's simpler. I'm not averaging a whole big list of numbers. I'm just finding the max and min, which is a fast operation, and averaging it. So actually the limit of this process, if I have boundary conditions, it's what's called L infinity harmonic functions, and these have been studied a lot, both in discrete and continuum setting. They're known as absolute Lipschitz minimizers because given boundary conditions, these will optimize the Lipschitz constant, and they will do it on every subgraph simultaneously. I may come back to that. This is the case P equals infinity, and it's somewhat easier to analyze. So the easiest case to analyze is P equal 2, the linear. The infinity case is easier than the other P. Okay, so as before, it's very easy to show that the limit, it's quite easy to show that the limit exists and you have a consensus. P equals 2 is called linear because when you differentiate P equals 2, the condition is the update is just the averaging, right? So when you do P equals 2, the update, so right, when you minimize Dirichlet energy, you get harmonic functions. So the function, say in the graph case, the function at the point is the average of the neighboring values. So it's linear. So P equals 2 is linear because when you differentiate, you're optimizing. The optimum is a linear condition, and so the equation that characterizes these is a linear equation. Okay, so I had this, right? So this is the case of general P, while in the averaging case, right, we had it in the beginning, right? We have linear. Okay, so why does the consensus exist? So in the case of P between 1 and infinity, we could just argue that the overall energy is decreasing in every step. So it's also the max is decreasing, the min is increasing weakly, but why can't they get stuck somehow separately? The reason is that the energy, the LP energy in general, will actually decrease in expectation in every step as long as we're not at a constant. So we cannot converge to some limit where the max and the min are different because so that's easy. And at P equals infinity, you can't apply that argument. So it's even a little more tricky to see why you converge consensus, but also, not that hard if you just want the qualitative thing. But we're interested in estimates. How long does it take or how fast the opinions converge to consensus? And so we measure it as before with oscillation of a function. It's the max minus the min. And tau p of epsilon is when we apply this LP dynamics, what is the time until the oscillation goes below epsilon? And this is random, so we will typically be interested in this expectation. Okay, and here is the first main result. There is a more sophisticated one I'll mention later that takes into account the degrees, but this is the behavior when we are just focused on the size of the graph. So the time to reach consensus, so let's ignore these log factor, which is less important, and just focus on the what power of n we have. So the time to reach consensus is behaving like n to the beta p, and in the next slide I'll mention that this is sharp, so this beta p cannot be improved. And how does beta p behave? It's the maximum of 2p over p minus 1 and 3. So if I plug in p equals 2, I get 4. Remember, we had n to the fourth for the easy case p equals 2. But this actually goes, right? So it explodes as p goes to 1, which is connected to the fact that you cannot solve the Dirichlet problem in L1. But as p increases beyond 2, so it monotonically decreases. And then there's a phase transition at p equals 3. Which is, we're used to, L1 is important, L2 is important, L infinity is important, but why L3? So this was surprising. And so this, right, at p equals 3, these two things are equal, and you get, and so the exponent decreases, but then it gets stuck at 3, and it goes there all the way, including p equals infinity. So even for p equals infinity, the answer is n cubed. So it's a little surprising that the convergence to consensus, we would think that averaging all the neighbors with equal weights is the fastest thing, fairest thing, but averaging, say, the highest and the lowest is actually converging faster. So that was a bit of surprise for me. Here is again our friend the barbell graph, which is the optimizer actually for all p. So for all p, the time to reach, say, if you start with opinions 1 on the right, 0 on the left, you want the oscillation to go down from 1 to a half, you need time which is n to the beta p. And I won't be able to do much, but I'll try to explain using the barbell why we might guess that at p equals 3 we get phase transition. That's kind of one thing that we understand actually from the barbell. Now, for p greater or equal 3, the barbell is still optimal, but you don't need the barbell. And in fact, the barbell matches the cycle. So on the cycle or on the path, you'll get the same behavior. So in a way, as you grow p, the density of the barbell becomes less and less important. You can think of growing p is kind of shrinking the effect of this barbell, and that in the end, it just can be replaced by a point, and effectively from 3 on. So, before I go to fancier theorems, let me explain this point. So this is like one calculation I want to do. So if in this LP dynamics on the barbell, this is the barbell Kn, we have Kn on both sides and a path of length n between them. So the total length here. So later I want to change the n to k, so I already have this k. But first think of putting an n here. So this is 3n nodes, but you'll allow me that. So we update the juncture vertex, so this V0. So, and suppose that, so we update it to the optimal value, delta p, and suppose that its neighbor V1 on the right had initially some gap of A, and F0, the initial condition is completely 0 on this graph. Then if we write down the equation to solve for delta p, how much is this juncture going to go up? We can write down the equation, and we find that delta p becomes this A times this power of n. Now, remember that if we were doing this with normal averaging, 0 sees about n neighbors with value 0, 1 the value a. So it would update to a over n plus 1, or just call it a over n. Okay? But here it updates. We can easily solve this optimization. It updates to a times n to this power. So in a way, you can think that when you put this clique of size n, it behaves, if we compare to the averaging case, it behaves like a clique of size n to the power 1 over p minus 1. So the linear case is something we always go back to because we understand that so well via the analogy to random walks. So in a way, this model with kn, kn is equivalent to the model. Okay, I just gave you some heuristic, but it's actually equivalent to the model with here on both sides, these cliques are of size k. And you see that as p grows, these cliques are shrinking. And but what happens at p equals 3? At p equals 3, right, this will become, this will, right? So I said this means this is like n to the 1 over p minus 1. So here. Right. So the point is exactly why does the path take over? So Benny already thought. So if I have if I consider classic case, the linear case, but I have k on both sides and n in the middle. What's the mixing time in this case? So again, in order to mix, the random walk has to cross from this side to this side. So first it has to visit the juncture vertex. This takes time k, or happens with frequency 1 over k. Once it's here, it has to make the brave step to the right. There are k neighbors following it to the left, only one to the right. So this again takes k tries before it will make the brave step here. Once it's here, it has to do the long crossing instead of coming back home. This has only probability 1 over n, so it costs you another n. So you get that the mixing time, the number of tries you have to do is k squared n, but that's not the full story of the mixing time, because once you start to make this, decide to make this brave path, it actually takes you a long time to do it. So this is just the number of attempts you make before you cross, but then the successful attempt costs you another n squared just to cross. So the true mixing time up to constant for this graph is going to be of this order. Okay, and you see that k equals root n is the critical point. So that's when crossing the path and getting out of this potential well are equally difficult. And that's where p equals 3 enters, because that will give the root n. So this is only explaining it heuristically and only for the barbell. The fact that, in fact, this works for all graphs requires some delicate analysis. And luckily, we have Fedit Nazarov on the team, who is the famous analyst who could handle this analysis. Okay, so this is what I wrote here, k squared n plus n squared. And I already told you the reasoning. And then, so if you follow this reasoning through, you get this value that we found just for this graph. And the point is, this is still the worst case. So this requires analysis, but maybe once you analyze the barbell, it's not surprising that this is the answer. So, and this explains where the phase transition occurs, at least in this example. Now, for the case p equals infinity, we have, I told you, n squared. Here is a more precise result, which is, so there's a logarithmic factor, and then n times diameter squared. So in particular, the worst case is n cubed, but it's more precise in terms of the diameter. And for every diameter, one can show this is sharp just using a graph like this. Okay, now I want to state the most serious theorem in the paper that took us, a year. And this is of work to prove. And this is what happens when you fix not just the vertices, but also the number of edges, or equivalently the average degree. So, right. So now look at the graph with n vertices and average degree b. So average degree is just twice the number of edges divided by n. So the answer here, I don't expect anyone to remember it, but beta p is the function we had before, max of 2k of p minus 1 and 3. Theta p is another function that you see here, and this one will have phase transition, and here we'll have two phase transitions, one at p equals 2 and one at 3, and this is, the final answer. You can see there are three different behaviors. So for p greater or equal 3 on all graphs, no matter what you assume on the degree, the answer is just n cubed. So same as on the path. But for p between 1 and 2 and p between 2 and 3, the answers are different depending on the number of vertices and the degree. And again here, in the case when we didn't fix the degree, we first knew what the example would be, and then the analysis of the upper bounds matched it. In the case of fixing the degree, the story was different. So, with all my experience in probability, I assumed that if I fix the degree, the extremal graph will be this. This is a graph, all of these are pleats of size d. There are n over d of them, and then we have a path of length n or constant n. I'm not fighting here with about constants. And then we have a path here, we wrote it 2n, and the same picture on the left. So I assumed this would be the extreme graph. I analyzed it. We got some bound with Gidi, which was this behavior. So we got that for all p. That's the behavior of this graph. And so I assumed this would be the worst case. And then Fedia was doing his magic with, LP inequalities, and he got it to match for p between 1 and 2, but for p between 2 and 3, his upper bound and our lower bound, didn't match. And I kept telling him, well, you have to work harder. We said, well, I milked this thing for all it has. And finally, he convinced me. And this turns out to be that really one has to build a different class of examples. So this is what we call the accordion graphs, which are the extremal graphs for p between 2 and 3. And this took some time to understand. So these, there are n over the anti-cliques here, and each one is connected to the right and the left one. And this is the extremal graph. Once you have it, you can analyze this graph. And finally, we saw that when analyzing this graph, this matched the upper bounds that Fedia had already derived. So I can't go into the details of the analysis, but anyone interested, it's not on the archive, but I can send you, or you can find it on my personal webpage. But if you don't find it, just, if you're interested in details, just write me. Not hard to find. Okay. And now, I told you the result for p equals infinity up here. So it's basically n times diameter squared with a log term. And there's a more precise result in terms of the cover time. So you don't have to assume here that the vertices are chosen at random. Suppose there's any way that the vertices are chosen, but you assume that no part of the graph is neglected, so you keep choosing all vertices. So tk plus 1 is tk is the kth time that the graph is completely covered, right? So if you know tk plus first time bigger than tk, that from time that the vertices will cover the Vj from, actually we want from from t, right, t sub k plus 1. This plus 1 is not in the subscript. So basically, we wait until we cover the graph k times, that's tk. And then we have an estimate, which turns out to be sharp, that the oscillation of ft decays like exponential of minus k over diameter squared. So you see that if you want this oscillation to really go down, you have to go to to the diameter squared number of cover times, and coupon collector tells us that each cover time takes n log n if we're doing random. But this is more general. So for instance, instead of updating vertices random, you could do round robin, right? You choose the vertices one by one according to some permutation and keep going. And then you'll get the same result, but without the log n, because you cover just in n steps. Okay, and this is one proof that I can sketch for you. The proofs for the LP involve, too many iterated Holder inequalities to present here. But the proof for infinity, it was interesting because the problem is how to find a good Lyapunov function or a good potential that keeps improving when you do these updates. So it's possible to find potential, but they improve very, very slowly. So how to find one where the improvement is substantial in terms of the potential itself, and this took a long time. Finally, the right potential is not a number, but it's really a function. It's the best concave modulus of continuity for the given value. So remember that the modulus of continuity, here we're applying it discretely, right? So we have the graph distance, and we want a function omega. This is just a function from integers to 0 infinity, where omega of the distance is a bound for the differences of the function, right? That's what the modulus of continuity is. We will only be interested in increasing such function, increasing omegas. They should vanish at 0, and we'll want them to be concave. So it's like one technical slide. I try to not to have many of those. Maybe it's easier to see it in this graph. So suppose I have already found some continuity, which is the red one. I'll come back to the statement, but the graph is easier to grasp. So I have the red one. And then after that, having that modulus of continuity, I do one more cover of the graph. So I visit every vertex at least once. When I finish that cover, the modulus of continuity improves from this red function to the blue function. What is the blue function? The value at any point in the blue function is going to be an average of values of the red function. So I'll come back. So let's say a good one to look at. So if I look here, right at 1, the new value of the new modulus of continuity is the average of the values here and here. So it's 0 and 0.75. It's the average of these two values, so we get 0.375. Because we are considering only concave functions, this definitely improves. This averaging yields a new concave function, which is better. So that's this formal statement here. So each time we cover the graph, we have a new modulus of continuity, which is the average of the old one at the neighbors. And it's also concave, so each of these improves. And that turns out to be an effective potential function that keeps improving. And maybe the details of this calculation are not so important. The key, so how do you, in the end, you want to measure the improvement. So we can't stay all the time with functions. We need some numbers. And the number we use is just the area under the graph of the modulus of continuity. So that area turns out to improve. So if you go over the details, it's easy to see that the area, so sk plus 1 is the area under the k plus first modulus of continuity, and it's improved by a factor of 1 minus 1 over 2L squared. L is the diameter of the graph. So each time we do this, we push down the area this way. So now it's from this it's easy to analyze that uh, after k times the oscillation will be small once you have the right potential function. But this is definitely not the first potential function we tried. It's like about number 100, and this one to match the lower bounds. L is the diameter. I don't use d because d we use for the degrees. So L is the diameter. So again, if I go to the graph, when I update, so for j between 1 and the diameter, we give this averaging, and for all values bigger than diameter, we just keep the constant, the value at the diameter. So that's how these functions look like. So they're constant once you go beyond the diameter. And so L here is the diameter. Okay, so I showed you all the extremal graphs which have these lower bounds. The lower bounds we prove are actually stronger in the sense that we show they hold for any choice of update vertices. So the upper bounds we prove when you choose the vertices at random. And part of the conclusion is you can, in terms of at least the worst case graph, you cannot do better by choosing the vertices in any other order. The most you can gain is the log factor. Like we already saw in the case for infinity, that you can gain a log factor by updating the vertices systematically rather than random. But that's the only possible gain because our upper bound, which is for random vertices, matches lower bound, which is for arbitrary vertices, up to this log factor. So the details of the lower bounds on the complicated graphs are complicated, but let me say something about the lower bound just for the cycle. What makes it a little non-trivial is that the lower bound, as I said, is proved for any update sequence. So consider a cycle with n nodes, right? Label 0 to n minus 1. Then for any update sequence, not just a random one, take time n cubed. So if t is less than this constant times n cubed, then the oscillation will be bigger than a half. And we choose a function which is 0 on one half of the cycle and 1 on the other half. So yeah, just draw this, right? So we take a cycle of length n, and we have a function which is, say, 1 on this side and 0 on this side of the cycle. And for that function, no matter what you do, the oscillation is at least a half. So that shows that the upper bound is tight, and for all p greater than or equal to 3, because remember, for all p greater than or equal to 3, the upper bound was n cubed, and this is what we get as the lower bound. And one thing that helps is on the cycle, the update actually doesn't depend on p, because the minimizer is always the average. So that's only true when the degrees are 2. But that actually simple thing is used. So even these sophisticated examples that I showed here, it actually uses the fact. So here we have a path, and here we don't have a path, but we have a path of clouds, and we use the arguments from the path, more sophisticated arguments on on these paths, even though they have some thickness. But that's actually the hardest part of the paper is the proof of the lower bound for this graph, I would say. But I'm going to just sketch the lower bound for the cycle, and that is because that is just averaging. That be understood via this mass splitting we discussed at the beginning. So the problem can be reduced to a question about the fragmentation process. So we have mass 1 at 0, and at every time we choose a vertex and split the mass there equally to the neighbors. Okay, so that's the kind of duality I discussed at the beginning. And then the statement is that when you do that, you need, in order to deliver a substantial amount of mass outside an interval, say minus RR, you need, so if you want to put, say, mass theta here, you need time which is R cubed. So until this splitting process has sent enough mass outside, it means that the opinion at the vertex V is only influenced by its local neighborhood. And we can, right, in this case, we choose V to be here, right? If the fragmentation process is locally supported, then the value here will be close to 0. And the value at the antipodal vertex will be close to 1. So we will be far from consensus. So understanding the rate of spread of this fragmentation is crucial here. Luckily, that's already been understood. And this is, so I'm going to switch to that in a moment and tell you that's something goes back to 2009 in the understanding of the overhang process. We had to do exactly this lemma. Some of you, I'm sure Benny has seen the overhang process. So I'll mention, so I'll have a few minutes and then I'll tell you about where this lemma came from, this lemma that says you need R cubed steps to send the mass. It actually comes from a nice story from some 15 years ago or more. Okay, but before, so I'll show you some slides from that, but I'll mention some questions. So in the case of L2, we don't just understand the worst case graph, but we understand the convergence time for each graph. So up to a log factor, the convergence time is just the inverse spectral gap of the graph times n up to some log factor. So the times n is just because we are doing one vertex at a time, and the mixing time of a graph up to log factors is just the inverse spectral gap. So you look at simple random walk, there's a transition matrix. It's a stochastic matrix. It has the highest eigenvalue 1. The next one is below 1, and that gap between them is the spectral gap. The inverse gap, which we also call the relaxation time, determines the consensus time. But for other P, we now understand exactly the worst case behavior, but we don't understand graph by graph. And one appealing conjecture, I think Junchi and Gan are close to it, but it's not proved yet, is that on any, say, family of graphs or nice family of graphs, increasing P should speed up the dynamics, or at least not slow it down. This we know for the worst case. So we know the worst case behavior improves as you move P up from 1 to 3, and then at 3 it stabilizes. But is it true on specific graphs, not just on the worst case graph? I don't know that. You know, including boundary conditions makes the analysis harder, but this is what I mentioned. Junchi and Gan have found the key to doing that. So that's substantial more difficulties that I don't go into at all. Another issue which we don't understand is how does the limiting consensus behave? So in the case P equals 2, there is a nice martingale. The average of the opinions at any time, weighted with the degrees, is a martingale. So you know that if you do this average, the limiting expected consensus has the same value as this average in the beginning. So that is nice. And then you can estimate the variance and see that the final consensus is actually concentrated near this average, unless the degrees are very wild. So if the degrees in the graph have a bounded ratio, then you get concentration of the limiting consensus near the weighted average. This is for P equals 2. We don't have any such understanding. What is the consensus you converge to for other P? Say for P equals infinity. Can you predict this without running the dynamics? You see all these values. Can you quickly predict it? And how concentrated is it? Okay, so those are the questions. And now I'm going to try and, can you help me with this computer? Let's see. I want to open another file. Yeah, maybe I can even manage it. Yeah, I think I can handle it. It's simple enough. Yeah. So I want to, in the last 4 minutes, tell you about the project where um, this bound came from. And it actually started with work of Patterson and Zwick. They were interested in this overhang problem. You have n blocks, and you want to put them over the edge of the table. How far can you go? This is often used as a riddle in high school, and this is the classical solution about half log n, but this is actually not the best. This is the best if you add an artificial requirement that you only have one block in every level. But if you remove that artificial requirement, you can do better. So already with 3 blocks, you can do that. Now, is this going to work? No. So this is work in general, even though this popular physics book claims it does, but it really doesn't. The diamond works, and so Patterson and Zwick first experimented with various small examples, both in theory and in practice, and then they analyzed the statics, and they don't have time, and they found a general parabolic stacks that are stable for all n. And this means that with n blocks, you can go to distance cube root of n. So instead of log n, which is the classical solution, if you do this, you can get the cube root of n. That was Patterson's Zwick, beautiful paper in Math Monthly. And then, Zwick came to visit Peter Winkler and me. We were in Berkeley at the time, and he asked, well, is this optimal? And he had a conjecture that this, so the oil lamp only improves by a constant. So the parabola is already. So he had a conjecture that this is optimal and that this will be somehow related to random walk problems. And in fact, he will exactly to this splitting game I told you about, where you start with a unit mass at the origin and you split it. And at every time you choose a vertex and split the mass there equally between the neighbors. So what we got to here in analyzing this opinion dynamics is exactly the same as the crucial. So this arose in the understanding the linear equations representing the statics of the block problem. And again, there are 2 Math Monthly papers, one just by Patterson and Zwick, one with other 3 authors that discuss this in detail. And I won't go through the argument, but you can find it in Math Monthly. It's a simple, but still non-trivial argument. You have to use not just L2, but also some L1 energy in order to prove this lemma. And I'm going to skip that and just mention that the same problem makes sense of spreading mass, makes sense in other graphs. And in a related later paper with Laura Floresco and Miki Rach, we analyzed this problem on other graphs. You have a graph, you have a unit of mass. How long does it take to get, say, half the mass to distance r? And there is a bound that is often but not always sharp, which is the volume of a ball times the expected exit time for random walk. But let me stop here.
Yeah, thank you very much. Questions?
So this may be a stupid question, but so the question is, was there any research on infinite graphs? And I mean by that, for example, you can take a unimodular graph with unimodular random coloring, and that you can iterate this process. It's almost like a factor of I did something, and then look at how this dynamics evolves.
Absolutely. So I don't know any analysis except for the peak with 2 case. So in the linear case, in that paper I mentioned from last year, we do study the infinite case. But when the initial conditions are IID, the problem is if you allow arbitrary initial conditions, even on the integers, you could have a situation where the initial conditions are 0 in a big interval, but then in a much bigger interval they're 1. And then in a much huger interval they're 0. So you oscillate at different scales, and this space oscillation will convert to time oscillation, so you will never have convergence. But one thing we proved there is that on all infinite graphs, if the initial conditions are IID and bounded, then you will get convergence to, at every point, you will have a limit. You won't get convergence to consensus because some nodes may wait a very long time, but locally you'll get convergence to consensus. So in any finite subgraph, it will equilibrate. So, but the case of other P, as far as I know, has not been analyzed yet for infinite graphs, and that's a natural place to continue.
More questions?
Thank you. It's not really a question, but an opinion. If you want me to read what I have written. So I do not know the theory of your talk, but I have been impressed by the link you make between what let me say, things like graph, opinion, neighbor, etc., to construct this mathematical theory. I appreciate it very much, and I would like to thank you.
Thank you.
Any other comments or questions or essays? Opinions? Okay, if not, then let's thank you all again.